welcome Orna to the online World Logic Seminar, AllSeminar. And Orna has been a great inspiration to me and to many people in younger generation. I think many of us have fond memories of her lectures at Mark Doberdorf and many lectures at conferences. So it is really a great pleasure to give the floor to Orna from the Technion to talk about automated program repair. Orna, go ahead.
Okay, thank you, Alexandra. This talk is about automated program repair using formal verification technique. Oh, it doesn't move, just a moment. My slides on, oh, okay, now they are moving. Model checking is the building block of formal verification technique. It's a technique that is given a system model and a specification and determine whether the system satisfies the specification or not. And in case the system does not satisfy the specification, model checking often return a counterexample, which is very useful. Formal automated repair, program repair, first applies model checking or a similar verification technique to find bug in the program, where bug is a program run that violates the specification. Then repair tool automatically suggests a repair where a repair changes the program code in a way that results in a correct program. I emphasize on the formal part in the title of my talk, because many of the repair work on repair are based on testing, but in our case, we will base our work on specification and on formal verification techniques. I will present two approaches to repair, which are quite different. Both are use formal verification techniques, but quite different from each other. One is about masked fault localization for program repair, and the other one use assume guarantee or repair. So let's start with the first one. It's a joint work with Rothenberg. And here we are given a Buggy program, and there is some kind of repair that results in a patch program that is correct. Where a patch program is a program where some of the lines in the program were changed so that the resulting program will be correct. And the problem with this approach is that there are many options to choose for locations to change and for changes to apply, so that it is difficult to cover the whole state space. Fault localization may help in this direction. Assume again that we are given a Buggy program with a violating run. Now, fault localization will point out to locations in this in the program that might be relevant to the bug. Repair then choose one or more location, will change them, and will result in a correct program. As said, fault localization should focus the programmer's attention on locations that are relevant to the bug. And if it is not well-defined, sufficiently well-defined, then it might be too restrictive, and then we might miss potential repair, or too permissive, in which case we will have too much extra work in order to cover the whole search space. And in most work in the literature, a fault localization algorithm return a set of locations that may be relevant. There is no guarantee that the returned locations are relevant, nor that every relevant location is returned. We suggest a novel notion, which is a masked fault localization. Before doing that, we will define the notion of repair scheme because it's relevant to the masked fault localization. Repair scheme identifies the changes to program statement allowed by the repair. For instance, in this talk, we will mainly deal with a repair scheme called smut for mutations, which allows syntactic replacement of operators on the right-hand side of assignment and conditions. So for instance, we can replace a plus by a minus, a greater than with a smaller than, a constant C with a constant C plus 1, and so on. Must fault localization now, a must fault localization algorithm returns a must location set for every buggy program and every bug, where a must location set contains at least one location from any successful repair for the bug. This means that it is impossible to fix the bug using only locations outside of this set. Or in other words, any repair for the bug must use at least one location from this set. It turns out that must notion depends on the chosen repair scheme, and it can easily be shown that a location set might be must for one repair scheme and non-must for another. In this work, we develop a fault localization algorithm. We prove that it is must with respect to smut, and we implemented it within the repair tool AllRepair and shows a significant speed up. So our setting is formal automated program repair, where a specification is given in order to distinguish between good and bad behaviors, and the program should meet the specification for all inputs. This means that it should pass formal verification, but in this work, we restrict ourselves to bounded formal verification, where we only consider execution or run of the program that execute loops only bounded number of times. Our setting again is a search-based program repair. We are given a buggy program and we are given a set of optional patches. And from this we get a search space which consists of all possible patches in all locations and all allowed changes. And now the method for program repair is generate and validate. So we generate a patched program, and if it is correct, then we send it to the user. And if it is incorrect, then we just throw it away. This is the validate part. I explained the algorithm for must fault localization by example. So let's look at this program that does nothing. It assigns t 0, then y gets the value of x minus 3, z gets the value of x plus 3. If w is greater than 3, then and so on. And at the end, there is an assert that requires that at this point, y will be greater than z. And here is the buggy behavior of this program. If we start from x equals 0 and w equals 0, then t becomes 0, y becomes minus 3, z becomes plus 3. And now when we get to the if statement, w is not greater than 3. So we jump right away to the assertion. And at this point, the assertion is violated because y is minus 3, z is 3, and minus 3 is not greater than 3. So here is the buggy program, and we want to build a must fault localization for this bug specifically. The first thing that we do is to transform the formula, the program into a program formula in an SSA, single static assignment forms. And what's special about the single static assignment is that every occurrence of the variable gets a different index. So for instance, here we see that y is assigned a certain expression on here. And this is using Y0, where the next assignment is assigned to Y1. Now, at the end of the if, we need to decide whether we are going to use Y0 or Y1. And for that, we use the condition on the if. We assign the condition to a Boolean variable G0. And now, at the end of the if, Y2 gets the value of Y1 if G0 is true, and the value of Y0 if G0 is false. And we see that on top of the formula describing the behavior of the program, we also have a negation of the conjunction of all assertion. And here we have the assertion that was violated. So now every assignment to the indexed variables correspond to a behavior of the program that violates the assertion. In order to compute the fault localization, we use a dependency graph. And the dependency graph describes the dependencies between index variables. So for instance, we have an edge, an arc between Y2 and Y0, because the value of Y2 depends on the value of Y0, but we remember that it's only on condition, not G0. So the static dependency graph just describes all possible dependencies between index variables. But we're interested in a more specific set of dependencies which are related to the specific bug that we have. This is the dynamic dependency graph. And since in our bug, G0 was false, we now take, for instance, Y2, and we take all the variables that can be reached from Y2 along edges that are marked either by not G0 or by true. If there is no annotation, then it is actually annotated by true. And now from this, we can compute the slice for this assertion that was violated. We see that the assertion depends on Y2 and on Z0, and we compute the slice of Y2. We see that Y2 depends on these three constraints, and the slice of Z0 depends just on this constraint. And now we also translate it back to program statement. So we end up with a set of program locations that are must fault localization. In the paper, we prove that this is a must set, meaning that if we do not change at least one of them, the bug will not disappear. We implemented the must fault localization within the tool AllRepair. AllRepair is based on generate validate, and it returns all minimal repairs from the search space based on smute. And minimality is with respect to the number of changes, or we call them mutations, applied to the code. So here is how it works. We take one patched program, and if it is correct, then not only we remove it from the search space in order not to get it again, but we also remove from the search space all those that are non-minimal with respect to this specific one. So we see that we reduce the search space in a certain way in AllRepair. But now we want to make AllRepair more efficient, and we want to reduce the search space both when a correct mutated program has been found like before, and when a Buggy mutated program has been generated. So when we generated an unsuccessful patched program, then we actually have, let's call it PM, and it contains a bug. And now we compute the mass location set F for PM with its bug. And we recall that if we do not change any of the locations from F, then the bug will stay. So now we can remove from the search space any mutated program that contains F and maybe more similarity to PM. So here it is. Now we take a program, it is incorrect, and now we remove from the search space this program and all the others which share with it the mass location set. And as before, if we get a good one, then we reduce the search space by removing the minimality. We have a third one that says that our fault localization AllRepair is sound and complete in the sense that when it does its pruning, it never eliminates a successful repair. So we are not going to lose any successful repair. I will go very fast over the experimental results because I want to go to the other approach fast enough. We have two benchmarks, the TCAS, which is traffic collision avoidance system for aircraft, and code flows, which is solution submitted by programmers to the programming context site code force. And code flows, the element there include loops, and therefore, since we are interested in bounded model checking, we use unwinding of the loop to 2, 5, 8, or 10 times. And it is not relevant for TCAS because it doesn't include loops. And the specification is just checking equivalent between the actual instance and a correct version of the program. We partitioned the experiment to 3 sets. The first one is the set in which AllRepair can deal with it, can return repair in less than 5 seconds. The dots along the x-axis are the instances, and the time is over the y-axis. And we see that for fast repair, there is not much gain or even no gain by adding the fault localization. On the other hand, let's look at the slow repair, which are AllRepair takes more than 240 seconds. And now we see that adding the fault localization gives us a lot of gain. In particular, we have 6 cases in which AllRepair timed out, where FL-AllRepair was successful in returning repairs. So just to summarize this part, we suggested a novel masked fault localization with respect to a certain repair scheme. It is must and not may, and therefore you must change at least one of the lines in order to repair the bug. And even though the fault localization is must, its computation is relatively cheap. And we obtained a significant speed up without losing any good potential repair. Okay, so now we move to another framework for repair, which is quite different. This is a joint work with Hadar Frankel, Corina Passareno, and Sarai Sheinwald. And the goal here is to exploit the partition of the system into components and to use some compositional model checking to verify small components and conclude the correction of the full system. And if a bug is found, to repair one of the components in order to obtain a correct system. So we are using the type of programs that we are using are C-like programs, consist of several components. Each component is described as a control flow graph. And in fact, we refer to the control flow graph as an automaton because we want to use an automata learning algorithm, L star. So let's see and the components communicate between each other using read-write over synchronized channels. So let's see how an example of how we can describe a program by an automaton. The program just read a password from its input. If the password is too short, is smaller than 999, then we read another password until we obtain a password which is greater than 999, and then we send it for encryption, and when it's back, we assign it to pass 2. In the automaton, it looks as follows. The question marks means that we read on the in channel an information to the variable X password. We then check whether the password is too short, and we read it again until it is long enough, it's greater than 999. We then send it to encryption. We actually send it out. This is the exclamation mark. We send the value of X password over the channel in code, and then over the channel get encryption, we get a value for X PW. If we have more than one component, then the components just interleave on their local actions and synchronize on the common channels. So here it starts with reading the password. It then goes over the loop until the password is greater than 999. It now synchronizes with the other component on the channel encrypt, and the value of X PW is assigned to the value of Y PW. Now Y PW double its value and send it back by synchronizing on the channel get encrypted, where YPW is assigned to XPW2. The specification is also given by means of an automaton. The automaton may specify sequence of communication actions that are allowed, but it can also set additional requirement by means of constraints. So for instance here, one of the requirements is that the entered password is different from the encrypted password. And we see that it appears here in the automaton by requiring that XPW is different than XPW2. The other requirement is that there is no overflow. And here it described by requiring that YPW after the encryption is smaller than 2 to the 64. If any of these constraints doesn't hold, then the automaton ends up in an error state. For the compositional model checking, we want to exploit the assume guarantee rule. And this rule, its goal is to verify that M1 composed with M2 satisfies the specification P. In order to do that, it replaces M2 with a small assumption, which is actually another automaton, but a small one, and checks whether M1 composed with A satisfies P. On the other hand, it also checks whether this assumption faithfully describes M2, which actually means that every behavior of M2 appears in A. And if the two premises holds, then M1 composed with M2 satisfies P. So here is the framework for the assume guarantee, a very rough description of the framework. We use automata learning L star in order to construct an assumption. We then check the two premises of the rule, and if either of them doesn't hold, then we go back to learn a new assumption. Altogether, this framework can result in one of two results. Either P holds in M1 composed with M2, or P does not hold in M1 composed with M2. And in the second case, we also get a counterexample, in which case we want to suggest a repair to M2.
Orna, can I interrupt?
Yeah.
Can you just say a little bit about the automata type AI? Is that a deterministic automaton or?
Yes, it's deterministic and it's complete. So actually the type of automaton that I described for the specification, just a moment. Here, this is the assumption is of the same type. It will be complete. And the completeness will be with respect to the constraints, not with respect to the communication actions.
So the language you are considering is somehow generated by these constraints. I mean, these constraints are some symbolic representation of an alphabet?
Yes, yes. So this is an important point that I wanted to mention later, but the language that will be learned by the assume guarantee framework will actually be over this type of alphabet. So the alphabet will be constraints, which will be referred to as syntactic element, and also communicating actions. And we will have a mechanism that will check whether a certain word is feasible or not.
And just another question on the next slide. The parallel operator, it doesn't generate like extra concurrent behavior or anything like this, does it? So
it's on the other hand, it usually restricts the behavior of M1 and M2. Here we refer to communicating programs. So when you see just one component, you see that it sends on receive or on any of the channels some information. But when it has an environment and the environment is not willing to do the counterpart behavior, then it will not be able to go on.
Okay, so it's fully synchronous, basically.
It's not fully synchronized. It's synchronized on the communication over the channels, but other than that, the local actions are interleaved.
Okay, there's also a couple of questions from Carlos Lopez Pombo. Maybe he wants to unmute himself and ask, or I can ask them.
Okay.
Let's see.
Okay, now I am mute. Thanks. I have two questions about the approach. The first one is if you tested this technique with an asynchronous communication models, like the ones used in session types and multi-party session types, communicating machines, so those communication approaches, in which the components has also this interface for sending and receiving messages, but it is done over buffers because the reception is asynchronous. But on the other hand, the data-aware versions of these formalisms are very close to the type of automata that you're using?
So this is something to consider. We developed everything for synchronous communication. And if the communication are not synchronous, then you actually, you're not sure when the information is going to get into the component. And it's something to think about it more deeply. I cannot just tell you if everything will work or not.
Sure, sure. Because I'm working a bit on communicating data-aware communicating machines, which are more or less the same formalism you're using, but with an asynchronous communication model.
Yeah.
And the second question is about these internal actions might lead to unsafe communicating patterns because a component might take a transition that might lead to places in which you are able to, in which these components are able to send certain messages and not others. And some other components might end up stuck waiting for a message because they are not aware of the internal transitions of the other component, the one that performed the transition. So it is the usual Milner's weak determinacy requirement for composition that forces you to have this same communication pattern on every possible branch taken by internal transitions. How do you deal with with these communication patterns that might be unsafe?
So we do not deal with it. We just assume that the computation may get stuck if there is no synchronous possibility. We do not assume that we have all possible channels at any step, at any state.
Mm-hmm. So, okay, so in some sense, your technique might find communication errors, like a deadlock because a component stuck waiting for a message that will no arrive because the other component took another branch or something like that.
Yeah, so for instance, if the specification requires that a certain communication will eventually occur and there is a deadlock that disallow it, then we will find it.
Okay, thank you very much.
Just another point, I will come back to the learning algorithm because it's not straightforward to extend the learning to this setting, but I want to talk about it later in the talk. And once we repair, we suggest a repair for M2, we go back to the assume guarantee paradigm and try to verify the new repaired system. So it's actually a kind of iteration between assume guarantee and repair. So let's look at the repair that we are suggesting, and we have two types of repair. The first one is a semantic repair, and it is applicable when the counterexample that we get from the assume guarantee contain a constraint. So let's look at some counterexample T, and then the first thing we do is to construct a formula in SSA form representing T. So for instance here, phi T consists of the following constraints. X PW is greater than 999, Y PW equals X PW, Y prime PW equals 2 to the Y PW, and so on. And now we get to the constraint that check whether XPW is not equal to XPW2, and the constraint that is violated is that Y prime PW is actually greater than 2 to the 64, and this happens when XPW was initially 2 to the 63. So we find a run which violates the specification. And now our goal is to use abduction so that we come up with a constraint C, so that if we add this constraint to phi t, then the two of them implies false, meaning that phi t will not, or t itself, will not be feasible anymore. We just eliminate it from M2. So as said, we want to find this constraint, and we want this constraint to be expressed by means of the variables of M2, because we want to repair M2. So what we do, we take not phi2, we want phi2 not to hold, and we quantify out the variables from M1, which is ypw and y prime pw. And after quantifier elimination and simplification, which were applied by Z3, we get the constraint that xpw must be smaller than 2 to the 63. And now we go back to the automaton and we add this requirement, this constraint on the automaton. And if we go back to the code, then it's similar to add assume that pass is smaller than 2 to the 63 in the code of the program. We have another type of repair, which are syntactic repair. This is applied when the counterexample contains no constraint. It's only a sequence of communicating actions and assignment, which is not legal according to the specification. And here abduction will not help to remove it because abduction just add another constraint, but it will not disallow this sequence of illegal communication actions and assignment. So here we have three methods to remove the counterexample. One is exact. We just want to remove exactly T from M2. This is done by writing an automaton that accepts exactly T and combine it with M. We take the negation of it and combine it with M2. We have two other syntactic repair. I will not go into that. Approximate will remove together with T other runs of the program, and the aggressive will remove together with T many more behavior of the program. So now we have the experimental results, which compares the three repair methods, and we see that as expected, the exact is usually much more expensive than the approximate and the aggressive. For instance, the extreme case is number 22, in which the exact repair eliminate one run at a time, and we have infinitely many counterexamples, and therefore it doesn't stop at all. Well, when we apply the approximate or the exact repair, they stop quite quickly. Here we also, on the other side, we also describe the size of the assumptions computed by the assumed guarantee. And we see that often the assumptions are much smaller than M2 itself. It's worth noticing that while we were using syntactic repair, when needed, we also use the semantic repair by abduction. So since the repair is going through iterations, then in some iterations, we may apply syntactic repair, while in other, we may apply abduction repair. So let's go a little bit into the L star algorithm. I will not describe it, but the main point about L star is that it is supposed to learn regular languages over finite alphabet. And our setting is infinite state program with first order constraints. So one decision that we made, that I already mentioned it following Alexandra's question, is that we learn word over alphabet, including statement in the code. So the alphabet in our word include assignment and communication actions and constraint. The other thing that we had to pay attention to is that L star expect a target language to learn which is regular. And in general, we could show that if we just take any, the same learning target as in regular L star, then it might not be regular. So what we decided is to learn the set of words which is accepted by M2. So just sequences of statement. So just to summarize this part, we suggested a learning-based assume guarantee algorithm for infinite state communicating program where we have to adjust the L star for handling infinite state systems. Since we were using L star several times because of the iteration between repair and the assume guarantee, we made L star incremental. It remembered where it ended up in previous iteration and just continued from there. So this added efficiency. The AGR, as we saw in the experiment, AGR is assume guarantee repair, often produce small assumption, much smaller than the original M2. And we suggested semantics and syntactic repair. And to summarize the whole talk, I presented two approaches to automatic program repair with an emphasis on using formal method technologies. Thank you.
Thank you, Orna. Usually we unmute everyone at the end and get to thank you. At the moment, I don't have the ability to unmute everyone, so I ask everyone who wants to unmute themselves, please do, so that we can clap for Orna. Okay. So thanks everyone. I just muted everyone again. So we will have some moments now to take questions. So if you have questions, please raise your hand, and I will then call names. So let's start with Peter van M. de Boos. Go ahead, Peter.
Yes, thank you. I was curious about the kind of specifications you are using. It seemed that they are of a partial correctness nature.
No, they are more like temporal logic, but they are safety properties in the sense that they don't have any fairness in them, but it's actually an automaton that identifies the desired behavior where some are non-desired and end up in error states.
Yes, but you want to prevent sort of triviality of repairing the program by having no behaviors at all.
Yes, actually, it's an interesting point. And when we were using the aggressive repair, we could end up with an empty set of program, which is undesired, of course.
So is there some measure that you are aiming for, some sort of minimal repair, which tries to preserve as much runs of the program as possible?
So we have the exact syntactic repair, which is an exact, it just removed the one counterexample that we got. And if we just use the exact, then we remove only bad behaviors. But it's not scalable. So sometimes we say we would like to lose this precision, but still get a program which is correct, but we may lose some of the good behaviors together with the bad. So there is a choice here. We give 3 options. Maybe someone can think of other as well.
Okay, thanks.
Okay, thanks, Peter. If there are other questions, please raise your hand or write in the chat. In the meantime, I'll ask one of my questions. So for the L star you used, would it have been possible? I mean, I understand you call it many times, so maybe you
Yes.
want to sacrifice precision a bit for the sake of efficiency. But do you think it would make sense to test a model that would more precisely capture the control flow of the program? So at the moment, your alphabet kind of takes the constraints as constants in some ways.
Yes, but at some point we check for feasibility of the word that we learn. So we do not give up precision because the learning behaves like L star. It checks, we learn M2. So we get a sequence of actions and we check whether it's part of M2. And if it is, then it is added to the assumption. If it is not, then it is added as not in the assumption. And then, as usual in L2, we have some kind of approximation of the automaton to get an assumption.
I see. And
incrementality means that if we, that what we noticed is that when we apply L star again, all the questions that we asked before are still relevant. So we can, if you think of L star as building a table of the information that it knows, then the table is still relevant, but the abduction adds another alphabet to the table because it adds another constraint.
Yeah, I see. And one question about the first approach. When you generate the search space, is this done also sort of on the fly and incrementally?
Yes,
or?
Yes.
Okay.
No, just we know what can be there, but we don't generate the whole state space because it will be outrageous. Yes.
Yeah. Okay. Thanks. If there are no other questions for now, I propose we go to the coffee break, and people usually have more questions in private. So let's thank Orna again for this great talk, and then we move on to the coffee break. So thank you very much, Orna.
Thank you.